Welcome grade 12s to physical sciences here at Mindset Learn Extra. You are here with our live shows with me, Megs, and TK, our teacher today, because I can't say his full name, so it's a little bit of a fail. But how are you?
Well, I'm fine. How are you, Megan?
I'm fantastic. Can you tell the grade 12s, which is, by the way, proudly sponsored by Macmillan, I cannot forget our sponsors, what we are doing today?
Well, today, Megan, we're going to look at photoelectric effect. And it's a section in grade 12 that they need to know before they go and sit for that very important exam. And one thing I like is that although this was done at grade 11 for today because of the new syllabus, what Tracy was doing basically,
it's like an introduction to this.
It's actually grade 12.
I did this like 4 months ago, so I actually kind of know what's going on. I was so impressed.
That's good.
Okay,
that's
well, I'm
good.
going to send you to the board so I can just tell our mindsetters what is going on here at the studios. Okay. So mindsetters, let me just tell you. Oh, will you please attend our fantastic board over there?
Yes, and I
Thank
begin
you.
to do
Okay,
my
well,
work.
mindsetters, we are doing fantastical things here at the Mindset Studios. Do you think you've got what it takes to be a future star here in South Africa? If you are between the ages of 16 to 21, which I hope now you are matric, so you're 18, will enter because it's on the website at mindset.co.za/learn extra with an X. And we can also find all the notes that you want, all these notes. I downloaded them. All the notes that you can, all the notes that you want there, and the videos on the webpage. And if you want to talk to me and TK now for this whole hour on the photoelectric effect, go to facebook.com/learn extra or hit me up at a tweet at the Learn Extra. But before I give to TK, I have to give a shout out to my gran. My gran is watching, my mother and father all the way in Durban, and my best friend watching right now, and my other best friend all the way in England. So enough about shout outs. Let's get back with it with the photoelectric effect.
Right, thank you, Megan. Let me start with the lesson for today. And like I said, we're talking photoelectric effect, so this is the lesson for today. And let's just have a look at what is entailed in this lesson. What are those key issues that you need to know when you talk photoelectric effect? Now, in this lesson, we're going to make sure that we describe to you what this photoelectric effect is all about. We are also going to explain the terms like photon, threshold frequency, and the work function. Now, we're also going to try and explain to you, show you some demonstration that will show us how photoelectric effect happens. So we will be looking at how we change intensity of electromagnetic radiation when light of certain frequencies is allowed to fall on a particular metal. Okay, and so in that way, we would have been able to show you how photoelectric effect happens. When that is done, remember that when we talk light, we're actually talking about something called an electromagnetic radiation. Okay, so earlier on, Tracy was teaching you about diffraction. Okay, the whole concept of the Huygens principle and other things. Now, that is about waves, or talks about light and giving you light as having a wave nature. But here we shall be bringing to you another nature of light or another nature of electromagnetic radiation, which seem to tell us as scientists that electromagnetic radiation or light has got a particle nature. Okay, now let's look at this. The first thing is, what is this photoelectric effect? Now, photoelectric effect is a phenomenon observed when electromagnetic radiation, so you see, sometimes I'm going to abbreviate that as EM. Please understand that I'm talking electromagnetic radiation. So photoelectric effect is a phenomenon observed when electromagnetic radiation of certain frequency falls onto a metal surface and causes electrons to be ejected from that surface. Okay. Now, let's have a look at something here, some kind of a demonstration for us here. Now, if I have a metal surface, so this represents a metal surface, this line here. Now, if I allow electromagnetic radiation of some sort, okay, say I've got, let me use that kind of color. Say I've got UV light, ultraviolet light, hitting this surface here, I will soon begin to notice that there are electrons that are being ejected from that metal surface. Now, what has caused these electrons to be ejected? At this point, we don't know. But by the end of this lesson, we will understand what has happened. And I'm also realizing that if I continue to bring more of this UV rays by means of increasing the intensity of that light, I realize that I'm getting more and more of these electrons getting off the surface of the metal. And because this happens through this process of photoelectric effect, we call this type of electrons that has been ejected photoelectrons. Okay, so these are photoelectrons. So if I have more and more coming, it means I would have more and more electrons getting ejected from that metal surface. Now let's look at another situation down here. Say at this point I've got some red light. So this is red light, as you can see it. So red. It is bombarding this metal surface. Say we kept the metal the same, the type of metal the same. Maybe we're talking zinc or we're talking sodium or whatsoever. So we're now bringing in a different type of electromagnetic radiation, which is red light here. Now, if you look at this, this shows you, or this drawing here talks to you about the wave of light. Now, if you look at this, you can see that the wavelength lambda is actually bigger. So here we're talking about a longer wavelength as compared to perhaps this situation here. I would have had something like that. Okay, so the frequency here, if you like, is higher. So I would say frequency here is much, much higher compared to the frequency here, which is much, much less. Now, what happens here when we do that, we bring in red light, we realize that no electrons are ejected. Okay? Now, no electrons are ejected. Let's try and see what happens if we bring more of the white, or of the red electromagnetic radiation in here. Now, allow me to use that color. That's what I have for now, and pretend that is also red, as you see. So I've got more and more of this hitting this surface, this metal surface. What is happening over there? I want to check as to whether I've got electrons being ejected. But what I realize is that no electrons still no electrons ejected. Okay? But this situation is different to that one where when I had electrons getting ejected, if I increase the number of those rays hitting that surface, I have got more and more electrons coming off the surface. Now we will have to explain this further in our lesson as we proceed. Okay? But just to help you understand a bit more of what is happening here, I want to introduce to you something very important, a terminology called threshold frequency. Now, what is this threshold frequency? Threshold frequency is the minimum frequency needed to cause electrons to be ejected from a metal surface. Now, this is a key word. This means that if you don't have that level of frequency, you will never ever get electrons ejected from that metal surface. Now, let me also tell you something important as well about this threshold frequency. The threshold frequency is a property of that electromagnetic radiation. In other words, for red light, I must have a specific frequency for that. It cannot be more than that. It cannot be less than that. Okay, so if we take this concept of threshold frequency back to what we're talking about here, we would be able to say that at this point here, the frequency of UV is either equal or greater than the threshold frequency. Allow me to put a T there, but let me just use a 0 there for threshold frequency, F naught. Okay, for these electrons to be ejected. But when I see these electrons moving up, which is something now I'm adding on what I'm saying, if I see these electrons being able to move off the surface, it means definitely that the frequency of the UV frequency, let me just write it this way, UV frequency is therefore greater than the threshold frequency. Okay, now we need to clear this up quickly. Threshold frequency must be a frequency, like I said, needed to cause electrons to be ejected from a metal surface. Now, in this case, we said for the electrons not to be ejected, it means that the threshold frequency or the frequency brought by the red light is much less than the threshold frequency. Okay, so now let's move on and look at some demo. I wish we were able to get this apparatus here. We call it an electroscope, the gold leaf electroscope. We're going to make use of it to demonstrate photoelectric effect like I've just explained here. So I'll be going through this demonstration with you. Now there is a diagram there showing you a gold leaf electroscope. Now you can see something is happening there. We've got the gold leaf electroscope. The leaves there are actually apart. They are moved. They've actually repelled. Something must have happened there. So say you charge this electroscope, because what we do with electroscopes, we charge them. Say you charge this electroscope, you charge it negatively, okay? When you charge it negatively, what will happen? If you charge this gold leaf negatively, it means there shall be negative charges on there, and there shall be negative charges on the leaves there. Now, we know that like charges repel. Like charges repel each other. Okay? So like charges repel each other. Hence, we are seeing the gold leaf, the leaves of the electroscope actually diverting like that or pushing each other away like that, because there's a force of repulsion between them, because both of them are carrying the same type of charge. Okay? Now, if we allow light of different intensities to bombard this surface, so there is the surface of the gold leaf electroscope. Let's check what will happen when we do that. Okay? So we allow ultraviolet light to bombard that surface. What will happen? Okay? And we vary the intensities of that light or ultraviolet radiation shining on that negatively charged electroscope. Let's observe what will be happening. I will be explaining that to you not so long. Next, we use specific intensities of UV for a long time. Specific intensity of UV for a long time on the same gold leaf, and we try to check what happens. So we're trying to observe what will be happening onto the gold leaf electroscope. Okay? Now let's try and look at the next part here. Trying to explain this. What have we observed? When you are using UV light on a charged electroscope, we have charged it negatively, And what does it mean for us to have charged it negatively? It means we have actually placed a lot of electrons on that, because the electrons are the particles that are carrying that negative charge. So there's a lot of electrons that are there that are causing the gold leaves to repel each other. Now let's have a look at what is going to happen here. We're going to actually note our observations here. When we are using UV, what will be the observation? We'll see that over time the leaves of the gold leaf electroscope collapse. And when they collapse, what happened? What actually happened with them? It means that you have taken that negative charge that was carried by both the leaves that led to them separated or moving away from each other. So you've taken out that negative charge, and then they are now coming together. Now, what is that negative charge? It means you have actually taken the electrons out of that electroscope. Okay? Now, our explanation here, it will mean that these electrons have been ejected from the surface of the gold leaf electroscope. Okay? So electrons have been taken or ejected, have been ejected from the gold leaf electroscope. Okay? Gold leaf electroscope. Now, when we have electrons ejected, we have what we call photoelectric effect. But we want to bring in a different situation here where we keep everything the same. We're still using a negatively charged electroscope, but we change the type of electromagnetic radiation that comes in there, or that is used to bombard the surface or the top of that electroscope. Now, we are now, instead of UV, we are now allowing red light. And of course, using different intensities again to shine on the surface of this gold leaf electroscope. And let's see what happens. Now, apart from what we have seen earlier on, with the red light, what happens is we see that the leaves of the gold leaf, those leaves, the leaves of the gold leaf electroscope, the leaves of the electroscope there stays the same. Oh, sorry, stays the same. Or stay the same, okay? The leaves stay the same. In other words, this time they don't collapse. Why? Okay, now that would mean that in this case we are not getting those electrons ejected from that surface of the gold leaf electroscope. And it does not matter whether we change the intensity, we increase it, we make it less, there shall be nothing happening on the separated gold leaves that are actually repelling each other. So that tells you electrons are not moving there or are not taken out. Now, then how do we explain this situation?
TK?
Yeah.
Do you mind if we go for a little bit of an ad break?
I think we should.
Just before you explain.
Definitely. So we will continue
so it gives them
from
something
here
to think about.
just after the break. That's fine.
Okay, cool.
Okay.
Well, mine said is there you go. Listen, go look at what TK said about the explanation. Write it on the Facebook page, and I will tell him what you've told me. And if it's right, then I'll give you like 2 thumbs up. Okay. So go for an ad break, and we'll see you afterwards. Welcome back, grade 12s, here on another live show of physical sciences doing the photoelectric effect. Can you believe it? Mr. TK is back with us. Yes, I know you guys are so excited that he's here. So I'm not going to waste any more time looking at me because you guys are all actually interested in what we're doing. So TK, can you please carry on with our explanation?
Thank you. Let's go ahead. We are trying to explain here what is happening with this zinc light, with red light on this electroscope, because we have seen that no electrons are being ejected. The leaves of the gold leaf electroscope stay as they are not collapsing. What must have happened? Now, there's something very important here to note, that even when we increase the intensity, still the leaves stay as they are. Nothing happens to them. They don't collapse. But then the wave theory tells us that when you increase the intensity, you are actually increasing the amplitude of that wave, and therefore you are increasing the energy. But then what will then this mean? Now, this tells us at this point that the wave nature of light doesn't explain everything about light. And therefore, as scientists, we need something else. We need another angle that we can use to explain what we have just observed. And that is when the photoelectric effect comes in. All right? Now, if you go back slightly to the UV, okay, when we had the UV, if you allow UV radiation to bombard that particular gold leaf electroscope for a long time, much longer time than you had, but we keep the frequency constant, what we see is that at the end, the gold leaf electroscope will have its leaves repelling again. Now, what would have happened at that point? It means all the electrons would have been ejected actually from that position, and therefore now both the leaves are carrying a positive charge. Positive to positive, like charges repel each other, that we know. Okay, now back to something very interesting in science. I have said here, we can't explain this. We don't have an explanation why the leaves of the gold leaf electroscope are not collapsing. Now, that brings us to photoelectric effect. And I have something for you here. I want to show you something here. Here is a demonstration of photoelectric effect. In here, here you are increasing, you're playing around with your intensity. So let me just bring it down to 0. Okay. So I have the intensity down to almost nothing there. And let me use red light there. Okay, there is red light. So this is a spectrum of electromagnetic radiation there. Now, if I start from there, okay, and let me say here I'm making use of the metal zinc, or maybe let me choose sodium. Now, what happens when I have red as my electromagnetic radiation, and I'm increasing the frequency, the intensity? This thing has to start working now. Let me work on this. Oh, there we go. It's moving now. So I'm increasing the intensity. You can see it's now at 40%, now 50%, and nothing is happening here. And over here, you can see that the intensity is actually increasing, but I don't have any electrons moving there. I continue increasing the frequency. It's full blast there. I've got 100% intensity, but I've got no electrons moving here. That tells you something. You have increased that amplitude in terms of increasing the frequency of red light, but you have not caused the electrons to move. Like if you had a situation like, say, look at what will happen if I have got that type of electromagnetic radiation there. I will have electrons moving if I have the intensity at that point. But even if it's not at that point, because the threshold frequency is actually reached, I would have electrons being ejected like that. But what does this mean? It means if your electromagnetic radiation has enough frequency, in other words, it has got the threshold frequency or more than that, you will have electrons ejected. And if you increase the intensity when you have a electromagnetic radiation that has enough frequency, it means you will increase the number of electrons that are going to be ejected. In other words, the photoelectrons that are produced or released per second increases. Okay, so that rate increases actually. So that's what we have there. I want to take out this demo so we can proceed with our lesson here. I want now to come to this one here, although I have slightly, in fact, explained it earlier on. If you allow UV light and you change now just the intensities of that, you allow it to shine on that negatively charged electroscope, what will happen? After a while, you will see the leaves. You will see the leaves collapsing. Okay? So the leaves collapse. This is what you will see. The leaves will collapse. But if you keep it there for a longer time, what did we say? We say the leaves will open up again if you keep it for a longer time. Opening up again because now leaves are positively charged. So that is basically positive. So the leaves are currently positively charged. Okay, so that's what is happening there. Now, moving on, I want us to come to this part here. The key concept that I want to talk about here involving photoelectric effect, and want to come into the level of calculation, trying to find out about this energy that is involved. Once you have work being done, you see electrons being moved, there must be some work done there, and where is the energy coming from? We want to answer that question here, and we will be talking about some calculations here. Now, one thing we need to be sure about or know from the onset is that the energy carried by electromagnetic radiation is quantized. And these things that carry this energy, we call them photons. Okay? Now that tells you, or that would mean that electromagnetic radiation consists of particles, and these particles are carrying energy, some pockets, some packets of energy, and we call them photons. Okay? So these packets of energy, like I've been explaining, we call them photons. And these photons carry energy. Each one of them carry energy according to that particular equation there. The energy of each photon is given by h times f. And what is h? H is what we call Planck's constant. So it's a constant. It is the same value used for every equation or every formula where we have got h. And f is the frequency of the electromagnetic radiation. Okay? And this is measured in hertz. So the unit of measurement for frequency is a hertz. Okay? And you would have seen that for the Planck's constant, the unit there is joules second. Okay, now another very important term that we need to explain, or concept that I need to explain to you, it's what we call the work function. Now work function is given by this. Look at it. We say, or we denote it, W naught. This is equal to HF naught. Now, what did I say F naught is earlier on? F naught is what we call threshold frequency. This is the minimum frequency required. So, threshold frequency. the minimum frequency required to eject electrons from a metal surface. So if you multiply Planck's constant with the threshold frequency, you get what we call the work function. Now, the work function is a property of a metal. This is a property of a metal. Okay? Now, this means that different types of metals would have different work functions. The work function for zinc, it's not equal to the work function for sodium. It won't be the same as the work function for magnesium, lithium, or whatever. Okay. Now, when the energy of the photons is less than the work function, we see that of a specific metal surface, we see that there shall be no electrons ejected. Okay? Now, remember how we defined the threshold frequency, the minimum frequency required for an electromagnetic radiation to cause electrons to be ejected from the metal surface. But once you multiply that threshold frequency by the Planck's constant and you get the work function, I'm saying to you the work function is a property of a metal. Now, work function will therefore be the minimum energy required to eject an electron from a metal surface. Now, as we look at this, we are saying that if this work function, or if the energy of a photon as it is carried by that particle hitting the metal surface, if it is less than the work function, we will see no electrons being ejected. But when the energy of the photon, the HF, is greater than the work function of a particular metal, we will see photoelectrons ejected. Okay? So electrons will be ejected there. Okay. Now, there's something that I want to take you to here, bring your attention to. Now, you see, things do not come in. Ideally, you may have the energy of a photon equal to the energy of, to the work function. But reality would tell us as scientists that the energy of a photon, usually it's either greater than the work function or less than the work function. All right. Now, in this case where the energy of the photon is greater than the work function, remember you need that work function, that amount of energy equals to the work function to dislodge that electron from where it is placed. But then, is the photon only bringing in that work function? No. The energy of a photon is HF, like we said. Now, this HF will be equal to the work function, which is the energy that has been used to dislodge that electron, plus the energy that the electron, the photoelectron, is going to use as it moves off the surface of that metal. So if I want to get my HF, okay, if I want to get my HF, which is the energy of the photon, it means that my HF will be equal to that work function plus the kinetic energy. But then we know what is kinetic energy, the energy of motion. It is half mv squared, so we would be able to say that HF is equal to the work function plus half mv squared, which is the energy of motion, kinetic energy. Okay, so that gives us some kind of an idea of how do we work with these energies, differences, the energy of the photon, the work function, the kinetic energy. And we'll be able then to use that to calculate to do some of the calculations, finding solutions to what has been asked to us. I think we should have some time to have a
breather.
yes, some breather for now.
Thank you, Mr. TK. Okay, well, mindsetters, you guys are understanding this concept, and I'm so happy for you guys. Keep posting. I promise we will answer and get to any of your questions. Okay, but quickly go have an ad break, and TK and I will be right back with you afterwards. Welcome back, Matrix Grade 12s, to our live show here on Mindset Learn Extra. So I know just in the beginning of the show I mentioned something about a competition, so let me just say it again so it's fresh in your mind and you know exactly what's happening here at the Mindset Place and Studios. So on our webpage we have this new competition called Future Stars. So if you think you have what it takes to be the next future star in South Africa, or you know of someone and they're just too quiet to tell you what exactly is going on in their life, but you know they have what it takes, then please go look on our webpage mindset.co.za/learn extra with an X, and it has all the details that you need to know about the competition, but it is only for ages 16 to 21, don't forget. Okay. And if you want, please keep posting on our Facebook page, which is facebook.com/learn extra, or hit me up on Twitter @learn extra. Well, that's enough for me. Mr. TK, please take it away.
Thank you, Megan. Now let's proceed. I've got some questions for you that we're going to look at and see how we can use those formulas that I showed you to calculate and give some solutions to some of these problems. Now let's have a look at question 1 here. Question 1 says calculate the energy of a photon. Now the first type of frequency that we're given here, or the photon that we're given here, is a photon of that frequency, okay? So it's a photon of 3.0 by 10 to the power 14 hertz. Now, energy of a photon, like we said earlier on, E is given by HF. Now, every time you are to do a calculation in physical sciences, make sure that the first thing you do is to write down that formula correctly in full. Okay, so that's what I have done here. Next, you substitute to it. What is H? H is Planck's constant. It's 6.63 by 10 to the power minus 3/4 times. What is F? The frequency of this photon is 3.0 by 10 to the power 14. All right? And at this point, you need to make use of a calculator. So let me have my calculator there. We've got the Planck's constant, which is 6.63 by 10 to minus 3/4 times 3.0 by 10 to the power 14. Okay, and what is my answer there? The answer is 1.99 by 10 to the power minus 19. So it's 1.99 by 10 to the power minus 19 joules. Now, this is the energy of a photon, and therefore the unit has to be joules, J, okay? So you also have to make sure that when you do a calculation, at the end of it, you put in the appropriate unit in which that quantity is measured. Here we're talking about energy. The quantity is measured in joules. Now the next question on, or the next sub-question on number 1 is we are to calculate the energy of a photon where the wavelength is that. Now this is a nice one because it makes us to understand that when we're talking frequency, we should be talking wavelength as well. Now, from the speed of electromagnetic radiation, which is a constant, oh my F there, but I'll leave it like that. Now, this speed of electromagnetic radiation, C, which we know to be a constant, which is at 3 by 10 to the power 8 meters per second, if we use that wave equation, we will be able to find out what our frequency is, because the problem we're having here is that we are given wavelength instead of frequency. Now, if we come back to this, remember, we still have to say that the energy of a photon is given by HF. Now, the energy of a photon given by HF, what is F? From our speed of electromagnetic radiation in a vacuum, C equals F lambda, we are finding out that from this, we can say that frequency is therefore equal to C divided by wavelength. Okay? C divided by wavelength there. Now, this is from there. All right? So here, it means I can be able to say, all right, for my F, I can substitute my F with C. That doesn't look like a C. It looks like an E. So I must get real C. C over lambda. Okay? And then, working it out, we would have this as equal to 6.63 by 10 to the power minus 34 times C is 3 by 10 to the 8 divided by what is our lambda. Now, another thing that we need to be always aware of, it's the issue of conversion of units. We are given this wavelength in nanometers. We need to work in meters. Now, if it's in nanometers, you are to convert to meters, you need to multiply by 10 to the power minus 9. Okay? So this will be 700 by 10 to the power minus 9. So in that way, we would have converted correctly. Now, at this point, you look for your calculator. All right? Now, we have got Planck's constant multiplied by that. So let me start by making sure that I have a fraction here, because I see I've got a fraction. This is 6.63 by 10 to the power minus 34, because that is my Planck's constant. That is multiplied by 3 by 10 to the power 8, C, so 3 by 10 to the power 8. And all of that is divided by, oh, I should actually come down here. I must go up there and delete what I did there. So I come down here. This is divided by 700 by 10 to the power minus 9. Okay, and what is the answer there? I'm finding my answer to be 2.84 by 10 to the power minus 19 joules. Okay, so the answer there is 2.84 by 10 to the power minus 19 joules of energy. Okay, so that is what the photon of that particular electromagnetic radiation will carry. That is the kind of energy it will carry. All right. Now, moving on, I'm coming to some interesting question here, and this is an exam kind of a question, and therefore let's see how we can attempt to work on it and ascertain ourselves that we can actually do well in that exam, grade 12 exam at the end of the year. Now, the question here says a metal surface is illuminated with ultraviolet light, so it's UV light, of wavelength 330 nanometers. Electrons are emitted from the metal surface. The minimum amount of energy required to emit an electron from the surface of this metal is 3.5 by 10 to the power minus 19 joules. Okay? Now, there is a sketch for you to see what is happening there. Now, the first question says, give one word or term for the underlined sentence in the above statement or above graph. Above paragraph. Now, what you're having here is they are underlining actually. It should have gone through up to that point. Okay? And what has been underlined here, if you remember what we have said earlier on in the lesson, is that The minimum amount of energy required to emit an electron from a metal surface is called the work function. So the answer that they are looking for here is work function. Now this is an exam question, like I said. It was on the paper a few years back. The next question says, calculate the frequency of the ultraviolet light. Now you have got the frequency, the wavelength of the ultraviolet light given to you there. What they want is frequency. Now we have just done something similar to that now. You can remember that we said from the electromagnetic radiation equation here, where we're talking about the speed of the electromagnetic radiation, okay? C equals F lambda, we can actually get what that frequency is. Therefore, if we say this is going to be, C we know is 3 by 10 to the power 8, this will be equal to F, that's what we're looking for, multiplied by what? Multiplied by the wavelength. And what is the wavelength that is given to us here? I think it's 320 nanometers. It's ascertained that it's 330. Okay, so that will be times 330 nanometers. We work in what? In meters, so we convert into meters by multiplying by 10 to the power minus 19. And therefore, from here, we will be able to say the frequency of ultraviolet light will be equal to 3 by 10 to the 8 divided by 330 by 10 to the power minus 19. Okay? So we have that, and then we can then bring our calculator and work it out quickly. Now there is our calculator. We have here 3 by 10 to the power 8 divided by 330 by 10 to the power minus 9. Oh, that must be minus 9, not minus 19. Did I write minus 19 here? That should have been, that must be to the power 9. Okay, so that's to the power minus 9, actually. So what did we get from our calculator here? So 3 by 10 to the 8 times 330 by 10 to the power minus 9, that, or divided by that, that should be equal to 9.09 by 10 to the power 14. So this equals to 9. This equals to 9.09 by 10 to the power 14. What are we calculating for? It's frequency, and therefore it must be measured in hertz. Okay? So that's what we had on this question 2 here. Let's see more of this question 2 because it continues at this part, at this point here. We're coming to number C. Number C says, calculate the kinetic energy of a photoelectron. Okay, so that photoelectron emitted from the surface of the metal when ultraviolet light is shined on it. Now, remember that here we're making use of the energy of the photon, HF. We know this will be equal to the work function plus what? Plus kinetic energy. Okay? Now, we now have our F here because earlier on we're not given F. Now, what is H? H we know, Planck's constant, 6.63 by 10 to the power minus 34 times the frequency. Now, remember the frequency that we have calculated down here? We found it to be 9.09 by 10 to the power 14. So that's what we need to substitute here to be able to find our solution here. So it's 9.09 by 10 to the power 14. That should be equal to, work function is given to us, I think it is here, 3.5. Remember, it is in the question. 3.5 by 10 to the power minus 19. So this will be 3.5 by 10 to the power minus 19 plus K, which is what we are looking for, kinetic energy. Therefore, finding or actually working out on this one, what we need is to get our calculator again, okay? And we say, all right, we need to look at this. We've got this part here that says we've got the Planck's constant. It's 6.63 by 10 to the power minus 34 times 9.09 by 10 to the power 14. And what do we get there? We're getting that at 6.03, you see you have to convert, you have to round that off. So 6.03 by 10 to the power minus 19. So this is 6.03 by 10 to the power minus 19. That whole thing should be equal to 3.5 by 10 to the power minus 19 plus kinetic energy. Therefore, your kinetic energy is equal to, all right, this minus that, okay? Because we're going to take this to the other side. So we will just go back to our calculator and say it will be whatever we have in the calculator there, whatever we have in this calculator here, minus what? Minus 3.5 by 10 to the power minus 19. All right? So let's see what we get. And that is 2.53 by 10 to the power minus 19. 2.53 by 10 to the power minus 19. 2.53 by 10 to the power minus 19 joules. So that is the kinetic energy of the photoelectron. That's how it is going to or that's how much energy that will be there for this photoelectron here. With a little time, I think, just little time that we had, guys, let's see, that we still have, let's see what we can do with this part here. It says, it's the same question, but saying now the intensity of the ultraviolet light, okay, is now increased, okay? What effect will this have on the following? Kinetic energy of the emitted photoelectrons? Will the kinetic energy remain the same, increase or decrease? You just choose here. Now, the kinetic energy of the photoelectron won't increase or decrease. It will stay the same. So we would choose here, remains the same. Remains the same. Okay? So the kinetic energy remains the same. Now, next one is, what will happen when we increase the intensity to the number of photoelectrons emitted per second? Write down only increases, decreases, or remains the same. This is going to increase, okay? The rate at which the photoelectrons are emitted is going to increase. So that increases. So that's how we answer questions based on photoelectric effect. I hope you enjoyed this lesson. This actually brings us to the end for today. Keep well, and from me, it's a bye-bye.
Thank you, Mr. TK. Well, grade 12s, that brings us to the end of our show. I am so sorry, but you know where to find us, facebook.com/learnextra, or download the notes at mindset.co.za/learnextra. So we just want to say thank you from TK and I. Sorry we couldn't get to all your questions. We really do apologize. Thank you, Macmillan, for proudly sponsoring our physical sciences show. We really appreciate it. And thank you, Calvin. I know Calvin was on our show since the grade 10 show, which was quite a long time. So thank you for revising, and we really want to say thanks from you to me, and don't forget about the Future Stars competition. Thanks, and that's all from me. Bye.